data on icy moons like Europa, Titan, and Enceladus. Today, he is a project scientist and a co-investigator on the InSight mission at Mars. He is also a co-I on Dragonfly, a future mission, NASA mission on Titan. So Mark is studying this very fascinating field of planetary seismology, and hopefully this field is entering a golden age right now thanks to the InSight mission that is active at Mars and future lunar seismology as well. And we are actually pretty lucky because those two topics are the topic of the seminar today. So Mark, everything works. So I think
great. Yeah, so thanks for the introduction. So today I'm going to be talking about two of the projects I'm working on. We've now been on Mars for nearly 3 years with the InSight lander, which is in the background. This is a partial list. I don't know actually when I made that author list. It could go on and on. The science team is huge, and actually, if you go to the next slide, you'll get a more or less complete list of everybody on the science team, which pretty much everybody should be on this list. So on the author list, because everything I'm talking about has been a massive team effort. One of the things I've learned about being involved in planetary projects is that you have to learn to adjust to very large author lists because everything takes a village. Next slide. So what we've done with InSight is really trying to move Mars into what we already know, into an area that's closer to what we already know about the Earth and the Moon. And so this is, you know, as I say here, it's the third planetary interior to be investigated in detail. So, you know, in the early 20th century, well, late 19th century, early 20th century, through the mid 20th century, you know, we defined all of those things about what the cross section of the Earth looks like. How thick's the crust? What's the mantle look like? How big is the core? All of those things that, you know, really defined the field of seismology happened in the early 20th century. So if you click again, we'll say that in the 70s, well, beginning in the 1969 and then through the 70s, the Apollo missions placed geophysics on the moon. And in particular, the seismic network of the Apollo landers operated until September of 1977, which was about 2 months after I was born. So I've literally been waiting a lifetime to get more planetary seismic data. So that was when we got our basic knowledge of the cross section of the moon. So now if you click again, we are looking to add Mars to that picture. And, you know, really what we're trying to do by looking at the suite of planetary bodies is looking at the big picture of how terrestrial planets, rocky planets form. And something you may hear me say, I call the moon a planet. I actually call all of the moons planets because to me, a planet is anything that makes itself around and behaves geologically. I don't care when it's orbiting. But don't tell the IAU that I said that. I still consider Pluto a planet too. Next slide. So the mission itself consists of 3 primary instruments. Over there on the left side of the screen, underneath the kind of UFO looking thing, that's the instrument I'm going to be talking about most today. That's SEIS. Seismic experiment for interior structure, and that consists of 2 seismometers, a very broadband seismometer and a short period seismometer that are hidden underneath a wind and thermal shield there. But we also had 2 other instruments, we are doing radio science with the medium gain antennas that communicate directly to Earth and basically do interferometric determination of the very fine details of the Martian rotation. And we also have the heat flow and physical properties package, HP cubed, which was designed to go down 3 to 5 meters and measure heat flow. I'll talk more about what actually happened with HP cubed later in the talk. Next slide. In order to have those three instruments function as we need, we actually need to have quite a bit of other payload associated with it. We have the robotic arm and its cameras. We love all the things the cameras send back. We have basically a full meteorological suite because for those of you who have ever looked at seismic data, you know, seismometers are really good at measuring quakes, but they're also really good at measuring pretty much everything else. Wind, pressure, magnetic variations, all of these sorts of things. So we put all these sensors on as well, in principle to support the seismometer, but in practice, we also get science out of those. Next slide. So we landed in November of 2018 on Elysium Planitia. It's the little dot labeled NSY there, which is not too far north of Gale Crater, where MSL there is listed. That's the Curiosity rover. It's an area that our landing site expert Matt Golombek called smooth, flat, and boring. We were looking for some place that was safe to land, close to the equator, so we could have solar power year round, and at a low enough elevation that we could land safely with the spacecraft we have. And when you added all those together, this was about the only place we could land. So that's our location. Next. This is an image of where we're landed. So we're the red dot over towards the left of the image there, and there's a relatively big crater 400 meters away. And there's other rocks labeled on there because the geologists love to name rocks that they see in the images. All the little arrows are pointing at secondary craters of a large crater that's off the side. It's called, I believe, Corona Crater, and all of the little ones are called Coronitas because people like to be clever in naming. Next slide. This was really exciting. Fairly soon after landing, the HiRISE camera, which is on the Mars Reconnaissance Orbiter, actually, took a picture of us from space. The kind of green thing in the middle is us. The Mickey Mouse ears are our solar panels, and the really bright spot out in front is actually the seismometer on the ground. So this was after we deployed on the ground. The bright spot is that wind and thermal shield giving us a saturated pixel, but it's amazing what you can see from space. Next slide. Before I get to the seismometer data, I just want to talk a little bit about the other stuff. So the RISE experiment, which I've already forgotten what that stands for. Acronyms get out of control in NASA. But basically, this is looking for very fine details in the spin axis and how it wobbles as Mars goes around. We call these small wobbles nutations. The analogy I always use is if you jiggle a milk jug and then feel how it kind of responds to your jiggling. That's and from that, how full the milk jug is. This is more or less what nutations are doing. And so this is one way of constraining the core. In case we weren't able to constrain it seismically, I'll get back. We were able to constrain it seismically, but the RISE data is consistent with that. Next. As I said, it's basically this is just using the radios we use for direct Earth communication. Most of our data actually goes through the orbiting satellites around Mars and then gets sent. We can send more data that way, but we have the capability of communicating direct to Earth, and we use these to basically do basic interferometric measurements to look at how Mars is spinning. There's the first order limits from the RISE measurements. They're working on publishing a new paper that's really refining that, but it's remarkably consistent with what we got from the seismology. So that gives us a lot of faith because these are independent measurements. Next slide. We do have the magnetometer on board, which gave some interesting results. Probably the first order result that was most interesting when we first landed is that the constant field, which is a function of crustal magnetism because there's no geodynamo on Mars, so it doesn't have a permanent magnetic field like Earth. But when we're on the ground, we're seeing the crustal magnetism from when it was magnetized early on in Martian history, when it did have a magnetic field. When we measured it on the ground, it was about an order of magnitude larger than what we can measure from orbit. That's not particularly surprising because from orbit, you don't see small wavelength variations. So this is telling us about that there are crystal field variations at spatial scales less than 150 kilometers to give us that much signal that's not seen from orbit. And there's a lot of time varying fields that people are continuing to look at to try to understand how they relate to magnetic sounding of the interior and interactions with the solar wind. Next slide. This is an old slide, but the whole meteorologic package consisted of a wind sensor, which is actually two booms that measure the wind on two different sides of the lander, Tavis pressure sensor, and with those two, there's a lot of really interesting things that seeing. One thing is, if you look there where it says dust devil vortices, there's all these little pressure drops we see all the time. It means that there are pressure vortices going over us, and we can see those all the time, but unfortunately, none of them have been big enough to clean off our solar panels. But there's a lot of other interesting waves that are seen and possibly even some infrasound signals. Next slide. For those in the audience who have ever installed seismometers, you know that these are really sensitive creatures. And we needed an extremely sensitive seismometer because Mars does not have plate tectonics. We knew we were not going to see giant events. And so the target was, 2.5 times 10 to the 9 meters per second squared per root hertz. That's if we convert that to displacement around 1 hertz or so, that actually gives us a displacement that's comparable with a hydrogen atom. Next click. So the design there plotted on a hydrogen atom was the black line, but we actually achieved better sensitivity than we needed, than we thought we needed, or about that black dot right there. Next slide. Next click. But in order to get that level of sensitivity, we really have to control a ton of different noise sources. So we have to worry about the intrinsic noise of the instrument, also temperature variations, wind, pressure, magnetic field, and understanding the lander vibrations next. So we landed on Mars in November 2018. This was our first selfie. The kind of goldish colored thing in the middle of the lander is size, and you can see right next to it is the wind and thermal shield. This was great. We're almost on Mars, but we're still a meter above the ground. Next. That's a problem because that's as close as a seismometer has ever gotten to Mars before. The two Viking landers actually both included seismometers. They're that little rounded cube there that's highlighted in the picture. And it's sitting there about 1 meter above the ground. One of the Viking seismometers did not work at all. It didn't uncage after landing. The second one did, and it recorded the motions of the lander very well. It recorded basically everything that was seen by the seismometer could explain by wind oscillating the lander. Next slide. So we didn't want to do that. We actually did make some measurements on the deck, and we saw a very similar wind response as the Viking lander. It was actually a little bit larger on InSight because we had great big solar panels that gave us a little more coupling in with the wind. So what we did is we deployed on the ground. Click again. I think it should start. Okay, so this is showing the installation process. It was actually quite involved compared to installing a field seismometer. Each one of these sols is a Martian day, which is a little bit longer than an Earth day. And you can see we had to put it out on the ground. We had to release it. We had to let the tether drop to the ground so the tether's not blowing in the wind. And then we had to open up this thing we call the load shunt assembly. This is a little thing to try to decouple us from tether changes due to temperature. It actually took us several tries to pull that thing open with the thing. You can see we keep trying, and then we finally move it. That was a lot of work. We're now 60 sols in. And now we're going to go and move the wind and thermal shield over, flies in there like a UFO. drop down, and slowly you can see the skirt fall down so that it shields us against wind coming in around it. And so Sol 70, we finally have an installed seismometer that's capable of giving the performance we need. So 2.5 months of work to install one seismometer. This is just how it has to work on when we're trying to operate on Mars, because if we have anything that we need to look at the data to understand how we did, we can send a command, we wait a day or two to get the data back to see how the command worked, and then we have to spend the time to plan the next commands. So every process that, split-second decisions you can make while installing a seismometer on Earth, multiply that times 2 or 3 days. And so that's why it takes 2.5 months to install a high-quality seismometer on Mars. And when I say high quality, of course, for people who have done high-quality seismometer installations, you wouldn't think putting it on a tripod on top of a pile of dirt would be the best place to install a seismometer. Next slide, see what else we got. I think it's going to show something on the left showing that opening the LSA. This was an interesting process. We had to explode little bolts and then pull it open. Next slide. And so they pulled it open next. And then put the wind and thermal shield next. I would normally skip through these quickly, but of course I can't share. I think I cut out one of the slides I normally include in here, but I just want to emphasize that even though that sounds like not a real wonderful way to install a seismometer on a tripod on dirt, in the band between 0.1 and 1 hertz, we're 1 to 2 orders of magnitude quieter than the best installations on Earth. And that's not saying anything about how people install seismometers on Earth or Mars. It's saying something about the noise of Earth itself. In that band on Earth, you're always seeing the oceans. And on Mars, we can get far quieter because the oceans aren't causing any noise on Mars. And so we actually, despite the fact it sounds like a rough way to install a seismometer, we get remarkably quiet, high quality data. And so the question is, that was always asked when we started proposing this mission, you're putting one station on Mars. Everybody took a class that taught them that you need 3 stations to locate an event. But of course, that's not true because seismic information gives us more than PNS travel times. So obviously with PNS travel times, most of the people in this audience probably know that if you look at the difference in time between the arrival of P and S, you can get distance. If you click again, it'll give a nice little illustration. Click again. And so, everybody knows that. What people often don't think about, but should know if they've thought about how seismic waves work, is that the other piece of information aside from PNS travel time is the polarization of those PNS waves. If you know how those waves are oscillating, we know the physics of how PNS waves work. And so we also know not only the distance, but we know the direction. And if you know the distance and direction, you have a location. Next. We have been able to locate several events. On many events, we still can't get good polarization, so we just have estimates of distance. We have a whole bunch of events. This was downloaded on Monday. There'd be a few updates since then, but we're actually just about hitting the point where we're going into conjunction with, starting basically today, we're going into conjunction, which means the sun is in between Mars and the Earth. And so we won't get data for a few weeks, which is always scary. That's actually the white bar. And what this figure is showing is each line going across on this figure is a spectrogram for a sol on Mars. And the warm colors represent times when there's lots of noise, and the purpley colors are when it's very quiet. The curvy gray lines are sunrise and sunset. This is all put to local mean solar time, so sunrise and sunset shift over the course of a Martian year because of orbital details. But you can see that Mars is remarkably noisy during the day, every day. It changes over the course of the year, but for a large portion of the year, which is the time period that's not the dust storm season, we get these great big purple patches, which are extremely quiet starting in the early evening and sometimes extending through the night towards morning. We have the band kind of in the middle above the black dashed line is the dust storm season. During the dust storm season, it's noisy all day long, and we don't see many events. All the symbols on here are events we've seen. They have we have all sorts of different categories of events, the low frequency family and the high frequency family. The low frequency family looks like events we're more used to on Earth, and those are mainly what I'm going to be talking about. But we have these high frequency events that are mainly above 1 hertz and sometimes quite a bit above 1 hertz, which I'll admit I don't understand. Some people believe they understand them, but there's a lot more work to be done on them. But basically, we see these during the times we have quiet time periods. When it's really noisy, we don't see much of anything. Next. Most of these events, we end up using spectrograms to find them. For those who aren't used to it, what I'm showing here, these are actually, we've got time on the vertical axis and frequency on the horizontal axis. I'm not showing everything here. And it's high frequency on the left, low frequency on the right. These are whole soul spectrograms. So you can see the noisy part in the middle of the day and the quiet times. If you click again, it'll highlight the events. They're often very subtle features. They're little caterpillars showing up in various noise band frequency bands. My screen just went dead. Okay, there we go. So these are pretty subtle features. These are some of the first ones we've found. Next slide. The first large event we saw was 173 sols in, so we named it SO173A. That's our naming scheme. We just have our sol on Mars and give them a letter for how many we see on any given day. And when I say it was the first large event, it was a magnitude 3.7, which is even for Texas is not particularly big, especially with injection from fracking and things like that, starting to get more and more of that scale. This is what the data looks like. It has pretty clear, if you click again, pretty clear P&S arrival. If you click again, you'll see there's a great big signal right there, which a seismologist might think is a really interesting phase showing up after P, but it actually is illustrating one of the challenges of working with data on Mars. This is what we call a glitch. The whole system has all of these thermal shieldings, but it's still moving through 20 or 30 degrees Kelvin over the course of a day, which is not the most ideal installation. And so lots of little thermal cracks and pops happen, and we see these glitches all the time. Unfortunately, it happened right in the middle of one of our big events here, but these are very recognizable, and we know how to adapt to them. Next slide. So over the summer, we finally got out basically all the results from our prime mission, which were delineating the major structure of Mars. We're extremely excited by that. We had a series of 3 papers come out in Science this summer. And basically, we looked at the crust, mantle, and core. So first, the crust, we got at so if we just have P&S waves, all we can determine is where the quake is. We don't have any information left over to determine structure. So we have to look for smaller wiggles in order to get to structure. In the case of the crust, what the primary thing we use to constrain that is receiver functions. We focused here on the 3 clearest events we had, which were 183A, 173A, and 235B. These are all similarly sized events, and they actually are all located in a similar area. I'm going to show you that later. But when you do receiver functions, which is basically trying to look for small S-polarized wiggles that happen after the arrival of the P wave, which is looking for conversions of P to S below our station, we see that that all of these events, they're noisy, and we use lots of different approaches, but they show 3 consistent arrivals. Those 3 consistent arrivals can be used for 2 possible interpretations of the crust. Those could be 3 different conversions below the station, and thus we have a 3-layer crust. And in that case, underneath InSight, the crust is about 40 kilometers thick. Unfortunately, that third one actually arrives at the same time that we would predict a multiple in the top layer could arrive, in which case we only have a 2-layer crust and it's around 20 kilometers thick. So those are our 2 possibilities. We are very confident in the top 2 interfaces. That third interface may be there, and if it is, it's pretty weak. But that's could be consistent with a very mafic lower crust, which has a very small contrast with the mantle. I personally lean more towards the 3-layer interpretation, but the data by itself doesn't tell us that. And then once we have that, I'm not showing the details here, but we can link that to crustal thickness across the planet through gravity modeling. And it tells us that the average crustal thickness using the range of models and the range of density structures to connect with the density, with the gravity modeling, suggests the average crustal thickness on Mars is between 36 and 72 kilometers. That's towards the thin end of pre-mission expectations. It's not unheard of, but it does eliminate very mafic, very dense crusts, which in order to match the gravity require very thick crust. Next slide. We also constrain structure in the mantle, and in this case, the extra wiggles we're looking for are phases that bounce off the surface of Mars an extra time along the path, or an extra time or 2. So phases called PP, PPP, or SS, SSS. They're very subtle features. If you look at the raw waveforms at the top, you can see, I wish I could show my mouse, but you can see there's slight bumps of energy coming in after the P onset and after the S onset. And if we just start, instead of plotting the raw waveforms, plot the envelopes filtered in different ways, we can start identifying possible arrivals of these multiple reflections off the surface. And these let us constrain the upper mantle structure. And the interesting thing is it implies that particularly for S velocities, there is a low velocity zone extending down to 400 to 600 kilometers or so, which is due to a thick thermal lithosphere. And that you see that negative gradient in S. It's on Earth, you don't get very many areas with negative gradients. It's because seismic velocities are always a competition between the increase of pressure causing higher velocities and the increase in temperature causing lower velocities. With a thick thermal lithosphere on Mars, the pressure gradient is less because the gravity is less. And if you have a thick thermal lithosphere, then you have a large temperature gradient across that because you have a conductive temperature gradient across that. So through a thermal lithosphere on Mars, you actually have the temperature effect beating out the pressure effect. And so you get this low velocity layer, which has interesting predictions. It suggests that we won't see direct S-wave arrivals for a fairly significant distance range. And we do see some events that seem to have very clear single arrivals that we interpret as a P wave and no S wave because we're in the S shadow zone. It also puts other constraints on the overall thermal gradients and temperature. It implies that the mantle is actually on the cool end of pre-mission expectations, which implies shoving quite a bit of heat-producing elements in the crust to match overall expectations. And it makes predictions on heat flow, which we would have had hoped to measure. Next slide. And then we also constrain the core radius from data. And once again, these are really tough wiggles to find. So we have our P and S waves, and what we're looking for here is SCS, S wave that bounces off the core mantle boundary. And these are subtle features. The one on the left is the raw data. That SCS label there would take a lot of imagination to believe on the left. On the right, it's polarization filtered to look for signals that are coming in nearly horizontally polarized, which is what we expect for SCS. And then in that case, it's actually relatively clear. This is for SO173A, which is the clearest event for this, but we actually see it on 6 different events. And it comes in at a consistent time. It's a difficult phase to spot, but we see it consistently in several events. And so that's consistent with a core radius of 1830 kilometers. That's it's pretty close to half the radius of Mars. It's also very much on the high end of pre-mission expectations. It's not outside of the allowable range, but it's very much on the high end. It implies that the core, to have a core that large, it implies the core has pretty low density, which means you got a lot of other stuff shoved in there besides iron and nickel. It also means that the core is big enough that you never reach lower mantle minerals that we see on Earth. You never get bridgemanite, which depressed a lot of geodynamicists who wanted to have a thin layer of bridgemanite at the bottom to do all sorts of crazy things, changing convection patterns. We don't see that. The core is too big. Next slide. The other thing we want to do is analyze tectonics. These are showing the first few events. This is actually from a paper in 2020. We've located many more events than this, but one of the interesting things is the vast majority of the events we're able to locate well happen in one area, Cerberus Fossae, which is an area of extensional faulting, very clear graben structures that have very young lava flows that have come out of them. And when I say very young, I mean geologically speaking, they're in the past 1 to 10 million years. We haven't seen any of them happen, but it is one of the youngest areas of volcanism seen on Mars. There's even some hints that you could argue some of the events we see are volcanic tremor. That's far from a unique interpretation of those events, but it is a possible interpretation. But it's really fascinating that we're actually, the events we've seen, most of the best events we've seen happened in an area where we thought we might see events, because there are also boulder trails in that area. To click again, I think I have a little explanation there. Oh, okay, well, this is the next slide. The waveforms are actually clear enough on a few of these events that you can try to do moment tensors. The farther one, that SL183A, is not well constrained at all, but the 235B and 173A are actually very well constrained, and they're mostly normal faulting, which is very consistent with what we would expect, particularly for 235B. It actually matches the orientation of the faults, which is great and surprising that it actually works. But those are exciting results. Next slide. Overall, the Martian activity rate is quieter than the intraplate areas of Earth, and far quieter than overall plate tectonic Earth. But higher rates than that seen on the Moon. This is actually pretty much what we expected. One interesting thing is, up until very recently, we had not seen any events that we would call over magnitude 4. Actually, over the last month, we've seen 3 events that would be just over magnitude 4, which is pretty darn exciting. But they're distant, and there's still a lot of things we're trying to understand about them. And so we're not ready to talk about them too much, but this is exciting that we are seeing some larger events. So we're now in our extended mission, and hopefully we'll see a few more large events. We're in the process of applying for extended mission 2, but it's unclear whether we'll have energy to continue to that. A little more on that later. Next slide. Quickly on the heat flow and physical properties probe, it was supposed to go down to depth and include a radiometer. The radiometer has worked wonderfully. The mole, not so much. Next slide. There was this wonderful oatmeal cartoon that was on the kind of time of launch. He was very excited about the mole, so I love that image. Next. But once we actually put it in the ground, it refused to go farther, so we pulled the superstructure off to see what we could see. And while we were trying to use the scoop to kind of press on the ground to give us a little more friction, it backed itself out. Next slide. That was a very sad day. The engineers did amazing work. We came up with ideas to actually push on it with the shovel while we were hammering and got it back down to the ground. Next. This is showing that process. This is over many sols. You keep pushing on and hammering a little bit, pushing on and hammering a little bit, pushing on and hammering a little bit. It got it down into the ground. Next. Yeah, that's showing the last little bit when we actually put the scoop at an angle to push a little bit deeper. Next. And then finally, we piled some dirt on top of it and hoped that it would have enough friction to go down farther. But when we hammered again, it still refused to go down. So this is the final state of the mole. It's buried, but it did not reach its desired depth. Next. Well, I'm not sure what happened to this one. It doesn't look like that. When I emailed it, it changed. It made it all a title. I don't know why. Anyway, our solar panels have become very covered in dust over the course of the mission. We actually just passed through aphelion, which is when we're at our biggest energy needs because it was the coldest, and our smallest energy input because the sun's the farthest away, so we don't get as much input. We thought we had to turn off the instruments to get through this, but we actually got some cleaning by doing something that sounds really stupid. We dumped dirt on ourselves during a high wind time period, and that dirt swept across the solar array to the left there and knocked off dust. And we got about 5% total over several cleaning things, about 5% total increase in energy, which was just enough to keep BBB operating. It's operating continuously right now. It's actually going to operate continuously through conjunction, and we'll get all the data in 3 weeks or so. Next. By keeping BBB on, we've seen 3 more interesting events on sols 976 through 1000. I'm not going to talk about these in too much detail. I'm just showing them here. They look like they're pretty far away, 135 to 140 degrees, and we think we're only seeing PP and SS because we shouldn't be able to see direct P and S from that distance. But we're looking for alternate interpretations and still trying to understand it. So this is interesting stuff that we're looking at now. Next. So summing up insight portion of this, it's a lot harder to install seismometers on another planet than it is on ours. But we are seeing amazing data, and we've actually, been able to deliver on all of the things we want to do of delineating the basic Martian structure. Next. You guys can look at all of this that you want. All the images are available as soon as they hit the ground. The science data the seismology data is available through IRIS. There's 3 to 6 month delay on that just for quality control, but most of that data, except those 3 most recent events, should all be available, and you can look at all of those. We're about to have another release here very soon that's going to have a lot of great events from once we came out of the dust storm season. Next. I'm going to go through this part fast, but this is exciting work that's happening now. We just got selected to put seismometers on the moon for the first time since the 70s. We'll be flying on a commercial lander to the far side of the moon to Schrödinger Crater next. And this is basically it's always hard when you send the slide, it doesn't show up quite the same as it does on mine. There's supposed to be text on the right, but the point here is this figure shows everything that we're trying to do with the Farside Seismic Suite. We're basically measuring on the far side of the moon for the first time ever. We've never made those measurements. Apollo is all on the near side, and all of the events located were on the near side. And there's actually question whether their events on the far side are the same as the ones on the near side, because there are major differences between the near side and the far side. It's a thicker crust. There's more heat producing stuff on the near side. There's a lot of differences between the near side and the far side. So activity may be different as well. We'll also look at local structure in Schrödinger Crater, which is a very interesting place with impact melt floored basin. It's actually a very clean crater. And then the background noise should be driven by micrometeorites. So those are our 3 major science goals. We're staying on deck in this case, so that's something to keep a close eye on. Next. Lunar seismology is very different than Earth. This is 2 1-hour records on Earth. You get this nice impulsive looking signal on this scale. Obviously, there are all those phases we are interested in are happening there on the left, on the top. But on this scale, you just see a nice impulsive arrival, which is actually probably just the surface wave that you're seeing there, but there's other stuff in there. On that same time scale, though, a moonquake looks like something that's just oscillating around forever. For that whole hour, actually, for the largest impacts, you could see the oscillations for 3 to 4 hours. And it's because the moon is dry and cracked up, and so there is a huge amount of scattering. So everything you see is scattered. The Apollo sensors were actually very good. They're very sensitive instruments, but the realities of 60s technology meant that the digitization was 7 bits. And so the noise floor was not set by the instrument, it was set by the digitization. And so many of the moonquakes look like the one on the bottom, which you would more likely think is a barcode than a moonquake, because it's just bouncing up 1 or 2 bits. Next slide. The figure on the right is showing all of the moonquakes recorded by Apollo. The circles are nests of deep moonquakes. These actually repeat on tidal time scales. The stars are shallow moonquakes, which are, some of them are quite large, up to a moment magnitude of around 5. But the orange box is outlining the near side, and you can see almost everything's on the near side. There's a couple deep moonquake nests that get right around the corner there and get onto the far side. This is our first chance to measure the far side. Likely what's happening is that we're not seeing the far side events because of attenuation in the deep mantle, but we can start constraining that with this data. Next one. Here's a picture of Schrödinger. It's beautiful. It's got a nice peak ring structure, and we'll try to do many of the similar things that we did to look at crust on Mars, on the moon. Next. The instrument we're landing is the vertical component VBB. It's 3 to 30 times more sensitive than anything Apollo had. And we believe the noise floor will be driven by micrometeorite impacts. So this is something that the Artemis program, which is wanting to land people on the moon, needs to worry about. If you're wanting to build a human habitation, you need to know how much is getting hit by these little sand-sized micrometeorites. Next. Big question that was asked is whether we can record without deploying to the surface. In the first half of the talk, I spent quite a bit of time arguing why we needed to do a very difficult deployment to get onto the surface of Mars. Of course, the real reason that is because the landers on Mars are very coupled in with wind noise on Mars. There is no wind on the moon. That doesn't mean there's no noise from being on the lander. There will be noise from being on the lander, primarily thermal. The moon changes temperature very greatly. At dusk and dawn, it will change temperature by a couple hundred degrees Kelvin. So that's going to give all sorts of cracks and pops at dusk and dawn, but the day on the moon is a month long. So dusk and dawn is a relatively short period of time. During the day, shadows moving across the deck of the lander is also going to give us thermal noise. But at night, we should actually be very thermally stable. So that should reduce that noise. And the question of whether you can couple through a lander structure to the ground motion is actually pretty easy to look at. We just stuck a seismometer on top of the engineering model of the Curiosity rover, which is, got wheels and suspension and all of this stuff that's trying to decouple it from the ground. We stuck a seismometer on top, the seismometer below, the spectrograms are on the right. You can see they are seeing basically the same thing, except at the highest and lowest frequencies. Basically, what we see is that below the lowest resonant frequency of the lander, the coupling is perfect. We have a transfer function of 1. So we'll lose high frequency information by staying on the deck, but we should see very good records in that 0.1 to 1 hertz band, which has been extremely useful for us on Mars. Next. Here's the seismometer that we're flying to the moon. It's the same. It's actually flight spares from InSight. But instead of it being a tilted pendulum, we're going to rotate it so it's a horizontal pendulum. Oh, back one. A horizontal pendulum measuring vertical motion. We can get a vacuum on the moon much easier than on Mars. We had to have a difficult vacuum sphere, which actually delayed our launch for 2 years on Mars. But on the moon, we get the vacuum for free. We just need to have a vent and a filter. And this is coming from our French collaborators at the French Space Agency CNES and IPG Paris. Next, we'll also be flying a 3-component instrument that's based on the SP seismometer from InSight. This is a new build, but it's based on the InSight sensor. It's micro machined silicon that gives the proof mass in the springs. We have to change the springs for lunar gravity, and we are doing now a Galperin configuration, which is 3 tilted identical sensors rather than a vertical and 2 horizontals. This is actually being delivered by Kinemetrics in collaboration with the UK at Oxford and Imperial College. Next. We are sitting in a pretty innovative design to let us operate through the night on the moon. The night is 2 weeks long, so this is not a trivial problem. We have a solar panel on the front where Schrödinger Crater is pretty far south, and so the sun doesn't get very far above the horizon, so we can have a horizontally mounted solar panel like this. And then we have these cube within a cube with insulation in between that lets us stay warm and toasty during the night. And just the 5 watts of energy coming out from running the seismometer continuously is more than enough to keep us warm. During the day, the heat is shunted off to the radiator on top. We have a patch antennas on top to communicate with a relay satellite. So the lander delivers us, but the lander won't live through the night. We will operate for 4 months. And so we have to be our own little independent spacecraft. We have our own comm system, we have all our own comm system and command and data handling and all of this stuff. And this was based on the CubeSat Marco that flew with InSight and returned our data during entry, descent, and landing. That's what we use for our command and data handling and power systems. Next. I'm not going to talk about this too much because I started a little bit late and I want to leave time for questions. But basically, we do all our communications during the day when we have solar panel, and then we're just quietly operating at night, gathering data and recording it on our own internal system, and then we send it back during the next lunar day. Next slide. One of the exciting things about this Farside Seismic Suite is we're actually co-manifested with this project called Litmus, which is led by Bob Grimm out of the Southwest Research Institute. It's my computer keeps trying to go to sleep. It's a heat flow probe and a magnetotelluric sensing system. And then Lucy is another electromagnetic sensing system that's aiming for astrophysics application. But this is basically the instrumentation we would want to include in a lunar geophysical network. So this is a test run of a lunar geophysical network, which we're pretty excited about. There's a lot of stuff we like to do for a lunar geophysical network that we can't do with FSS. We're only using one station, doing the best we can, but it lets us test out a lot of things we'd like to do for LGA. Next. So yeah, so this is wrapping it up on the moon, and I left a few minutes for questions. We're going to outlive the commercial lander delivery, and we're looking at we have our science objectives that we're doing, and you know, the key to making this work is that we have a really great design that lets us keep operating after the lander dies and lets us operate through the very difficult to operate lunar night. It means a lot of our mass is batteries, but we're able to do it. Okay, I'll stop there.
Well, thank you, Mark. That was very fascinating. I will take. There is one question from the chat that I will take first because it was first, and then I will take questions for the people online. So the chat question was: have you identified meteorites impacts on the InSight data?
The quick answer is no, we have not. We had hoped to. There was actually a crater that was identified in orbital imagery that was less than 100 kilometers away, but it was a tiny crater, maybe 1 to 2 meters in diameter. Based on our estimate, that was right on the limit of whether we could detect it or not. And we haven't been able to identify that in the data. I will say, this is very speculative, but we did have one event on Sol 986 just recently that had these weird, so it was a high frequency event, but it was associated with these weird low frequency dispersed signals. The first thought was, oh, these are surface waves, but they don't make any sense for surface waves. They're very clean arrivals, and the amplitude is inconsistent with the fact that we actually haven't seen surface waves on any other event. One interpretation of those is that it's some weird instrumental noise that we've never seen before, which is possible. Another interpretation is that it's infrasound signals that get dispersed in a waveguide in the Martian atmosphere. And that would mean that the whole event could actually be an impact. And if that is the case, it would be about 100 kilometers away. And those may be impact signals. We're desperately looking at that. I'm giving you a hint of something that is not ready for public distribution though, because it could also very well just be instrumental noise. This is the fun stuff. Every time we see something on Mars, it's something nobody's ever seen before. And so it takes us a while to convince ourselves what we're looking at or what we're not looking at.
Okay, thank you, Mark. We have a question online from Tim. Tim, go ahead.
Great. Yeah, thanks for the talk, Mark. It was really interesting. I had a question about the InSight crustal structure results that actually came up with my research group as we were reading these papers. So in the two interface model, as I understand it, the top interface is regolith to bedrock, and then the lower interface is crust to mantle. But in the preferred 3 interface model, what's that middle interface? Like, what is actually the physical structure that's giving the reflections there?
Yeah, and that's a good question. I don't know the answer. I mean, it could, you know, it's pretty common on Earth to see, you know, significant chemical changes within the crust that give you pretty distinct mid-crustal interfaces. You know, this could be some sort of underplating. You know, I don't know. I don't have a quick answer. You know, it's sharp enough that you would want it to be a chemical, you know, an actual compositional change, which I don't know exactly why that would be there. But you know, it's certainly not unheard of for a crust to be complicated and have you know, compositional layering. You know, like I said, if that is a third layer in the crust layer, it's got to be very mafic because it's a very small contrast with the mantle. But of course, that's not surprising. I mean, the Martian crust we know is pretty mafic. If you just take the surface, if you just take the Martian meteorite compositions and the observed surface compositions, it comes out extremely mafic and extremely dense. We are actually, the densities of crust to match what we're seeing, to match with the gravity data, implies that the crust actually can't be as dense as you'd get just by taking the Martian meteorites and assuming a thermal structure and doing it. You get a far denser crust. So there has to be quite a bit of, it could be that the crust is overall more felsic than what we see at the surface, or it could be that it's just very porous. I think it's actually probably pretty porous down to 10 kilometers, and that's the first interface. There's some modeling that suggests that you could keep pores open to about that depth. That's work that Francis Nemo and others have done. But I don't know what that next interface would be. It would presumably be compositional, though.
What I guess one sort of quick follow-up that I'm wondering if anybody's thinking about is a wildly speculative idea that it's, I'd have to go back and look where the landing site falls relative to the proposed northern basin, right? Like the impact origin of the hemispheric dichotomy. Like if you look at Jeff Andrews Hanna's like mapping that out, are you within it?
We're just north of the dichotomy boundary, very close to it, but so just north of the dichotomy boundary.
So I wonder if that middle interface is that ancient basin floor that then's been filled in, and then it's regolith and so on. Yeah, neat stuff.
Okay, I will have, and that might be the last brief question. We have one question from the sparse attendance here in the meeting room at UTIG. Go ahead.
Yeah, it's Alexei Portnov. I'm proud to be one of the 3 persons here in the room of 4. So I have a general question and less general after that. So your rover, or sorry, your lander is not the only one working on Mars right now, right? There is a Perseverance, there is a Chinese, as far as I know, and from Saudi Arabia. Do you guys somehow communicate with those rovers? And do you hear them with your seismometer? And it doesn't sound very silly or fantastic. So you're listening to natural seismicity. What about the induced seismicity? For example, if you have a source on one of the rovers or landers somewhere far away from you, like this Schrödinger Crater, and then you would hear it with your seismometer. Is that possible?
Yeah.
In the future?
The short answer is no, we can't hear anything from how far away the other landers are. None of them are particularly close. Curiosity is not that far away. They're actually pretty much due south of us, which actually makes for interesting. We have to negotiate satellite passes because we're always on the same satellite path. So either they get data or we get data. But we actually we had one of our collaborators, Ben Fernando, who just finished up his PhD at Oxford, spent a lot of time coordinating efforts to see whether we could see the landing processes of Perseverance and the Chinese rover. And the short answer was we thought it was a small percentage probability that we could see it, and we tried to listen. You know, we got all the data we could during the time period when the landings were happening, and we didn't see anything. It's a long way away, and you know, a rover going around is pretty noisy if you're standing right next to it, but if you're, you know, a few thousand kilometers away, it's not much signal. So it was possible that we would see some of the, you know, the masses impacting the ballast masses that get ejected. So that's basically an impactor. We thought we might be able to see those, but as we look at the data, there's no clear signals associated with that.
Okay, and for the enthusiasts who like to keep it long, we can take the last two questions, actually, if you want to stay online. First is Sean online.
Yeah, great. Thanks, Mark. That was a really great talk. I guess I have a question on the lunar one, on the Schrödinger Crater work in particular. I'm curious if there's been some modeling about what sort of ray paths might illuminate the local structure, whether they need to be shallow quakes or you can get it from some of the Farside quakes to help with that. Oh, sorry, near side.
Well, it'll be, you know, so the short answer is probably teleseismic quakes are easier. It's going to be really challenging is the longer answer, just because of how scattered the lunar data is. You know, if we get very clean data, the issue is to do receiver functions, we need the 3-component data, which is the SP sensor, which is not as sensitive as the VBB. And so we're probably only going to get, you know, order 10, 20 events that are clear on that. And it's going to be challenging. We're going to do the best we can, but it's going to be challenging to do that. We'll also look at autocorrelations of the BBB noise. And I didn't show that, but for Mars, we also looked at autocorrelations. And for the crustal structure, and Alan Levander down at Rice also published some stuff on autocorrelations. And we're in very good agreement for the shallow structure, for looking at autocorrelations, for looking at crustal structure. You can actually see stuff that looks like those 2 interfaces. There's not clear that you can see the 3rd interface and the autocorrelation, and so we'll be trying that. But autocorrelation is a little bit of magic,
yeah.
And a lot of processing magic, I guess, to convince yourself it's real. And so we really hope we get a few good receiver functions, but it's going to be challenging on the moon.
Great, thanks.
Thank you. And we have finally one last question, which is on the chat from Nicolas. But Nicolas, if you want to unmute and ask your questions live, go ahead.
Yeah, okay. So I noticed on the map your proximity to Elysium, and I think that's where some of the younger lava flows on Mars are. So I was just kind of wondering speculatively whether it was possible in the future, or whether it's a future mission entirely, whether you could discriminate between regular Mars quakes and Mars quakes that are derived from like the movement of magma.
Well, so we haven't really seen much that looks like it's coming from Elysium, or really anything that we would identify as coming from Elysium. But like I said, actually, most of our events are coming from Cerberus Fossae, which is young volcanic. It's not a mountain, but it's had young lava flows. Actually, my dream and what I'm trying to push is that we have a network of small landers with SP level sensitivity that land in the Cerberus-Fossey area. It wouldn't be sufficient for a global network because those SP sensors are not sensitive enough to detect global events. But if we're landing in an area where we know there's seismicity, then we could have a little network there and look for, you know, what ones look volcano-tectonic, what ones look like they might be tremor, what ones look like they're, you know, we could start actually looking at the dynamics of an area that we know is active now. I think, you know, if we do hard landers that have impact-hardened sensors, that we could do that relatively affordably. And, you know, when I say relatively affordable, I mean, you know, a few $100 million. But compared to the $8 billion going into Mars sample return, you know, it's relatively affordable to get some other stuff besides Mars sample return going on in the next decade.
Yeah, I'm getting excited thinking about that possibility now that you brought it up. That would be golden.
I would love it, and I'm trying to push it to people. We actually just had a Keck Institute of Space Sciences workshop last week, where that was one of the mission ideas we're thinking. We're trying to think of innovative ways to do Mars surface science, an affordable way of working around Mars sample return, and I really think that's a really promising mission concept.
All right, thank you.
Okay, well, thank you, Mark. That was a very interesting seminar. Thank